You've probably typed something like this hundreds of times: lspipe grep, a simple command that filters files by name. But have you ever stopped to wonder, what does that little vertical bar actually do? It looks simple, but behind that single character, the kernel performs a hidden dance of system calls. It allocates memory, duplicates processes, rewires file descriptors, and sets up a shared communication channel, all before your command even starts running. In this video, we're going to trace the entire journey. We'll start with file descriptors, the foundation of all Linux I/O, then we'll meet the pipe system call, which creates a kernel buffer. We'll see how fork duplicates a process, how dup2 rewires its connections, and how exec replaces it with the program you actually want to run. By the end, you'll understand every step of the choreography that makes the Unix pipe one of the most elegant abstractions in all of computing. Let's begin. Before we can understand pipes, we need to understand file descriptors. Every process in Linux is born with 3 open file descriptors. File descriptor 0 is standard input, or stdin. This is where the process reads data from, usually the keyboard. File descriptor 1 is standard output, or stdout. This is where the process writes its normal output, and by default it goes to your terminal. File descriptor 2 is standard error, stdir, used for error messages. Think of file descriptors as numbered slots in a table inside each process. Each slot points to some I/O resource, a file, a device, a socket, or, as we'll see, a pipe. When you run ls, it writes the directory listing to file descriptor 1. That output appears on your screen because fd1 is connected to the terminal, but here's the key insight. These connections can be changed. The process doesn't know or care where fd1 actually points. It just writes to slot 1. And that is exactly what pipes exploit. Now let's create a pipe. In C, it's just 2 lines. You declare an array of 2 integers and call pipe. The kernel fills in the array with 2 file descriptors. fd0 is the read end, fd1 is the write end. What happens inside the kernel? It allocates a buffer in kernel memory and creates 2 file descriptor entries that point to it. Whatever you write to the write end can be read from the read end. It's a one-way data channel. Think of it like a physical tube. You push data in one side and it comes out the other. The data maintains its order, first in, first out, and the kernel handles all the buffering for you. But here's the thing. Right now, both endpoints belong to the same process. A process talking to itself through a pipe isn't very useful. We need a way to hand one end of the pipe to a different process. And that's where fork comes in. But first, let's look at what this buffer actually looks like inside the kernel. Let's zoom into the kernel and see how this pipe buffer is actually implemented. The kernel uses a ring buffer, a circular array of memory pages. By default, a pipe gets 16 pages, each 4 kilobytes, for a total of 64 kilobytes of buffer space. The kernel maintains 2 pointers, a read position and a write position, that chase each other around the ring. When a process writes to the pipe, data goes into the buffer at the write pointer, and the pointer advances. When another process reads, data comes out at the read pointer, and that pointer advances too. When the write pointer reaches the read pointer, the buffer is full. When the read pointer catches the write pointer, the buffer is empty. This design is beautifully efficient. There's no need to copy data around or shift elements. The pointers simply wrap around when they reach the end of the buffer. And the best part? The kernel handles all of this transparently. The processes on either end have no idea they're communicating through a ring buffer. They just read and write to file descriptors. We have a pipe with 2 endpoints in a single process. Now we need to split it across 2 processes. Enter fork, one of the most important system calls in Unix. When a process calls fork, the kernel creates a near-perfect copy of that process. The child gets its own address space, its own stack, but crucially, it inherits a copy of the parent's file descriptor table. This means the child process now has access to both ends of the pipe, the read end and the write end. And both the parent and child's file descriptors point to the same underlying kernel pipe buffer. Now we have what we need, 2 separate processes connected by a shared pipe. But there's a problem. Each process has both the read and write end. We need the writer to only have the write end, and the reader to only have the read end. Keeping both ends open in a process can cause issues. For example, the reader would never see an end of file because its own write end is still open. We need to close the unused ends, and we need dup2 to do the final rewiring. This is the rewiring step. dup2 takes two arguments, an old file descriptor and a new one. It makes the new FD point to the same thing as the old FD. Think of it like unplugging a cable from one socket and plugging it into another. In the writer process, we call dup2 of the pipe's right end onto FD1. Now stdout, FD1, points directly into the pipe. We then close the original pipe file descriptors since we don't need them anymore. In the reader process, we do the mirror image. We call dup2 of the pipe's read end onto FD0. Now stdin reads from the pipe. Again, close the originals. After this rewiring, the writer process doesn't know its stdout goes to a pipe. It just writes to FD1 like normal. And the reader doesn't know its stdin comes from a pipe. It just reads from FD0. This is the beauty of the Unix abstraction. The processes are completely decoupled. Each one thinks it's talking to a terminal, but the kernel has secretly connected them through a 64 kilobyte ring buffer. Now let's put the entire sequence together. When you type lspipegrep.txt and hit enter, here's exactly what happens step by step. Step 1. The shell calls pipe, creating the kernel buffer with a read end and a write end. Step 2. The shell calls fork to create the first child process. This child will become ls. Step 3. In the child, dup2 wires the write end to stdout, closes the unused read end, and calls exec to replace itself with the ls program. Step 4. The shell forks again to create a second child. This one will become grep. Step 5. In this child, dup2 wires the read end to stdin, closes the unused write end, and calls exec to become grep.txt. Step 6. The shell itself closes both pipe ends because it doesn't need them and calls wait for both children to finish. Now ls writes file names to its stdout, which flows through the kernel's ring buffer, and grep reads them from its stdin. Two independent programs connected by 64 kilobytes of kernel memory. 6 system calls, 1 elegant abstraction. That's the Unix pipe. What happens when the pipe buffer fills up? Let's say the writer is producing data faster than the reader can consume it. As data piles up, the ring buffer fills. When it's completely full, all 64 kilobytes occupied, the writer's next write call blocks. The kernel puts the writing process to sleep until the reader consumes some data and frees up space. The reverse is also true. If the reader tries to read from an empty pipe, it blocks, sleeping until the writer produces more data. This is automatic flow control. No configuration, no manual buffering, no coordination code. The kernel just handles it. If the producer is too fast, it slows down. If the consumer is too fast, it waits. There's one more important detail. Pipe BUF, which is 4096 bytes on Linux. Writes of this size or smaller are guaranteed to be atomic. If multiple processes write to the same pipe, their data won't get interleaved, as long as each write is within pipe BUF. Larger writes may be split, allowing other writers' data to be mixed in. It's a simple but powerful guarantee. Everything we've discussed so far involves anonymous pipes. They're created by the pipe system call and only work between related processes, a parent and its children, because the child must inherit the file descriptors through fork. But what if you want to connect two completely unrelated processes? That's where named pipes come in, also called FIFOs. You create a named pipe with the mkfifo command. This creates a special file in the file system. You can see it in a directory listing with a P at the beginning of the permissions, but it's not a regular file. No data is stored on disk. When one process opens the named pipe for writing and another opens it for reading, the kernel connects them with the same ring buffer mechanism we've already seen. Same 64 kilobyte buffer, same blocking behavior, same flow control. The only difference is the connection method. Instead of inheriting file descriptors through fork, processes connect by opening the same file name. This makes named pipes perfect for communication between daemons, scripts, or any processes that don't share a parent. Let's step back and appreciate what we've seen. That simple vertical bar, the pipe symbol, triggers a precise sequence of system calls. Pipe creates the buffer. Fork duplicates the process. Dup2 rewires the connections. Exec launches the programs. And the kernel's ring buffer moves data between them silently. Each piece is simple on its own, but together they enable something profound. Any program that reads from stdin and writes to stdout can be connected to any other. No shared libraries, no APIs, no protocols, just bytes flowing through a buffer. This is the Unix philosophy in action. Write small programs that do one thing well and connect them with pipes. It was invented by Doug McIlwain at Bell Labs in 1973, and it remains the backbone of every shell session today. Think about that next time you type a pipeline. Cat, grep, sort, unique, head, each one oblivious to the others, each one doing its job. Connected by nothing more than 64 kilobytes of kernel memory and 50 years of elegant design. Thanks for watching.